Hello everyone. In this last lecture, I want to go over an overview of the general circulation models. So first thing is we have seen the simpler model, then models of intermediate complexities. Now this will serve as an introduction to the GCMs, the general circulation models, which are towards the more highly detailed computationally intensive spectrums. So a GCM, a general circulation model, is a numerical model that simulates the three-dimensional circulation of the climate system. So, three-dimensional meaning actually over the x-axis, over the y-axis, over the z-axis and at any particular time. So, 3 dimensions integrated over time. Fundamentally speaking, the GCM will solve the fundamental physical equations which will govern the atmospheric motion, so motion of air in the atmosphere, the oceanic circulation, so flows of water in the ocean, and similarly the transport or the transfer of energy, of moisture and of the momentum. These models are used for several of these things: climate variability, climate change projections and process understandings. When we say climate variability, what we mean is how the climate is fluctuating over time given the same conditions of natural and anthropogenic forcing. So, these are the variations in climate over time. So, variations in climate will become the variability. Then we have the climate change projections. So, now we can change our forcing, the anthropogenic forcing or the natural forcing, and given the variability from above, how much actually is the climate changing over and above this variability. So, that over and above the variability becomes the climate change part. Finally, we have the process understanding. So, now as we have seen, we have focused on energy balances and radiations, but we have the chemistry also, CO2 injection, then associated greenhouse gas effect increase, how the temperature changes with changes in CO2. So, then we have other processes, for example, we saw phytoplankton capturing carbon, carbon sinking, how each of these processes can influence future climate or the variability in climate. Maybe these processes are important, maybe these processes are not important or can only influence the climate to a certain extent. So, the climate models or the general circulation model can also help us understand the impacts of different processes on climate variability as well as climate change. As we have seen earlier, there is a climate model hierarchy, of course. We have different levels of complexity. At the lowest complexity, we have the energy balance models. After that, we have the radiative convective models. Then we have the Earth system models of intermediate complexity. So, we have seen these models as well as these models. Then we have the general circulation models, which are describing the physics. Even beyond that, actually, we have the Earth system models, meaning they will model everything of note in the Earth. They will model the physics, they will model the circulation, they will model the chemistry, they will also sometimes model the human development scenarios, the population scenarios, the associated economic or industrial development scenarios. What if someone makes this decision? So, what if someone makes another decision? And how that influences the emissions of gases? How does that emissions of gases influence the temperature or the physical conditions? How those physical conditions then influence the climate in terms of precipitation, in terms of temperature, general weather patterns, climate extremes if they can. So, there are so many different levels at which the models will exist. Of course, and as we have seen earlier, the increasing complexity then leads to description of more physical processes. We also then have higher spatial resolution. Of course, when we have more processes described at a high resolution, we end up with the high computation cost. So, if we were to plot this in x and y, we have the details of the description and the number of processes. Here we have, to the far right, we have AGCMs, OGCMs, atmospheric, atmosphere, ocean, the earth system models. In between we have 2D and 3D earth models of intermediate complexities. Then we have 0 and 1D energy balance models. Here we have the number of interactive components of the climate system. So, as we see, these earth system models are actually at the top apex of both number of interactive components as well as the details of the description and the number of processes that are included. So, then we come to the question of why the 3D models are needed, and the most important and actually the maybe the only or the main answer is climate is governed by 3-dimensional processes. It is governed by 3-dimensional fluid dynamics. Therefore, if we want to accurately model these 3-dimensional movements, we require 3D representation. 3-dimensional representation of what? 3-dimensional representation of atmospheric circulation cells, 3D representation of baroclinic eddies, also 3D representation of the ocean currents and the overturning circulation. So, we need all of these representations to be done in 3 dimensions to be able to model the climate. Similarly, or concurrently, the lower dimensional models cannot represent the horizontal heat distribution. They cannot represent the vertical coupling between the surface and the free atmosphere, whereas the GCMs explicitly resolve the longitude, latitude and the height. So, longitude, latitude and the height, and are able to explain these processes. A typical general circulation model will consist of an atmospheric GCM, AGCM, an ocean GCM, OGCM, a sea ice model and a land surface model. So, if we look at a general grid, we have here, this is land. So, we have the lithosphere grids. As we go towards the ocean, we have the oceans. Now, lithosphere we do not need to resolve in different layers. We may have an active soil layer and then lithosphere, and we have vegetation above this active soil layer. Sometimes we have topography, mountains or such kind of landforms, and we have ice sheets over the land. When we come near the oceans, we have oceans. So, we have maybe like shallow oceans and then shallow and deep oceans, and we have oceans described in so many layers. We have sea ice above the oceans. Now, and then above the oceans and land, we have the atmosphere. So, these are different atmospheric grids. Now, all these components will exchange heat, they will exchange moisture, they will exchange momentum. So, for example, here we have the horizontal and the vertical exchanges, and we have of course the radiative fluxes over the whole globe. So, here it is a representation, but these fluxes are happening everywhere. So, the coupled GCM, coupled meaning the atmosphere coupled to the ocean, coupled to the sea ice, coupled to the land surface model. This will simulate feedbacks within the climate system, and this becomes a highly detailed GCM. So, these climate components are coupled through flux exchanges at the interfaces. For example, when it's atmosphere ocean, they may be exchanging heat, they may be exchanging like fresh water or sort of water precipitation, exchanging the momentum. When it is atmosphere and land, we may be talking about exchanges of radiation, exchanges in evaporation, through water runoff. When it is ocean and sea ice interaction, we may have exchanges of heat and salinity. Now, this sort of coupling between atmosphere ocean, atmosphere land, ocean sea ice allows for the simulation of what? Of the different climate feedbacks, what process change in climate may influence any of these, influence in any of these may in turn affect the climate again. This may by modeling in GCM, we may also be able to check the variability within these systems, how they vary seasonally, how they vary monthly, how they may vary interannually. When we increase our time span, we can see how there is a long-term climate evolution. So, how these variations occur over a very long time frame. So, these kind of things can be modeled in GCMs. Now, when we talk about these GCMs, the GCMs are based on the primitive equations of geophysical fluid dynamics. What are these equations? These are the equations that describe first the conservations, conservation of momentum, conservation of mass, conservation of energy, and the conservation of water vapor. Equations are derived from the Navier-Stokes equations in a rotating sphere, and then these equations are solved under the assumptions that are appropriate for the applicable large scale atmospheric and oceanic flows. So, for example, the momentum equations will describe changes in wind velocity. This would be due to pressure gradients. So, of course, wind will move from high pressure to low pressure system. The Coriolis force, which will try to move the wind directions. Then other forces acting on the wind would be gravity and also the frictional forces at the surface. On large scales, the motion of wind is strongly influenced by the Earth's rotation. So, the Coriolis force then causes the geostrophic balance in the mid latitudes, and this causes the atmospheric and oceanic circulation. So, for example, if we have different pressure systems in the horizontal P, P minus delta P, P minus 2 delta P, P minus 3 delta P, a wind parcel moves from high pressure to low pressure system. Now, as the particle gains velocity, the Coriolis force will try to turn the particle to the right. So, the particle sort of turns here, such that at some point a geostrophic balance is reached, and the particle then moves in this direction. So, this is sort of the geostrophic balance that we are talking about, geostrophic balance in mid latitudes. And this of course then causes our rotational, atmospheric and the oceanic circulations. The GCMs typically will apply the hydrostatic approximation. This assumes vertical pressure gradient will balance the gravity and the vertical accelerations would be small. This is generally valid where motions at horizontal scales are much larger than the motions at the vertical scales. This will filter out sound waves, allowing for larger time steps of integration and a greater computational efficiency as a consequence. Then we have the continuity and thermodynamic equations in these GCMs. The continuity equation, which we already did in the previous week, the derivation of the continuity equation, this ensures the conservation of mass, which is of course a very important property. Then we have the thermodynamic energy equation. This equation will govern the temperature changes. These changes could be due to adiabatic processes happening in the atmosphere, the level of radiation that is being received or emitted, also the latent energy that is being released at any level in the atmosphere. So, when we look at conservation of mass and the thermodynamic energy equations due to these processes, together this and these equations will govern or link the vertical motion of air in the atmosphere, the temperature evolution in the atmospheric layer, as well as the atmospheric stability, which is of course governed by these motions and how energy is distributed or redistributed, something that we can recall during our lecture on radiative convective models, how convection redistributes the energy to achieve the observed lapse rate. So, together mass conservation and description of these thermodynamic processes will govern and link the vertical motion, temperature evolution and the atmospheric stability. Now, when we talk about radiation balance, radiation is of course, as we know, the primary driver of the climate. Now, our GCMs compute the shortwave radiation, which is the solar radiation, the terrestrial longwave radiation. Now, when we are computing these radiations and using and parameterizing these radiations, these radiative transfer schemes then account for different gases in the atmosphere. Then clouds, of course, which are very important in terms of climate governing radiation absorption, reflection in general and the whole climate feedback. Similarly, aerosols have to be accounted because these are also important components. All this radiation will of course then provide the heating rates for the thermodynamic equations that we were talking about. So, then these are all coupled. Now, when we have these GCMs, we may also need to do some spatial discretization. So, the GCMs will solve equations on a discretized spatial domain. So, as we have seen previously, we can discretize something like a x, y and t plane into a constant spatial resolution delta x and a constant time span delta t, and have m delta x describing a point, n delta t describing a time point. So, this was one example of discretization. So, the GCMs likewise will solve equations on some sort of discretized spatial scales. Now, there are two main approaches that can be used. One is the grid point model, which would be Cartesian model, Cartesian planes, or latitude longitude based discretization. Then we can also have spectral models. When we talk about the grid point models, they will solve equations at discrete locations in the grid. So, they will solve models at one grid location, another grid, another at discrete locations. Whereas, the spectral models represent the fields as the sum of spherical harmonics. Now, okay, so this is okay. Now, why this discretization is important? Because this affects the accuracy of the model the numerical stability of the model, also the computational cost. If we have a large spatial grid, the computational cost may be low. The numerical stability may be easier to satisfy, because if you remember CFL criteria, U delta T by del x. So, if delta x is high, maybe we are approaching more stable conditions depending on the numerical scheme of solution, as of course. But when we do these compromise, our accuracy may also get compromised. If we want higher accuracy, we may be influencing the computational cost. So, we are talking about some trade-offs. Now, of course, we have seen this, that GCMs use very different vertical coordinate systems. These choices may include pressure coordinates, then the sigma, which was dimensionless coordinates, also an hybrid sigma pressure coordinates. Now, the hybrid coordinates may follow the terrain near the surface. It may transition to pressure levels aloft. In general, the vertical coordinate choice will influence the representation of the topography, the boundary layer processes, also the numerical accuracy of the simulation. So, in all these, you are saying numerical accuracy a lot of times. That is because in all these models, we have to make a compromise often between the time step of integration, the spatial resolutions, and we have seen also previously in the previous week that many numerical schemes will have the numerical diffusion term, and our goal is to have that numerical diffusion, which is actually a error introduced by the integration, to be as low as possible. But that depends on what is our resolution choices, what are our choices in solving the model. So, as one of its components, the vertical coordinate choice can also influence the numerical accuracy of solution. So, as we have seen, the GCMs will integrate equations forward in time using different time stepping schemes. So, some of the common schemes are our explicit scheme that we have seen, like CTCS, centered in time, centered in space. They can be semi-implicit. They can be leapfrog schemes, different leapfrog schemes with some filters. However, the time step is constrained by numerical stabilities, our CFL criteria, U delta T by del x. But then we do this, but if we make some, or the modelers, when they make some hydrostatic approximations, sometimes sometimes larger time steps are also okay. So, it depends on case by case. Now, when of course we have to remember that many climate processes can occur at smaller scales than the model resolution, and these processes then have to be also represented. Examples include, which happen on very small scales, could be cloud formation, convection, turbulent mixing and the gravity waveguide. These parameterizations then will relate the unresolved processes to the resolved variables. So, there are a lot of things that are being explained about GCMs, and this is the challenge and a good thing of GCMs. Challenge is that we have to represent so many things, and the good thing is that since so many things are represented, the simulations might produce more realistic results depending on how the parameterization is, of course, but there is the potential. The subgrid processes then strongly influence our climate simulations. Some important subgrid processes include deep and shallow convection, cloud microphysics, boundary layer turbulence. All of these then influence our energy balance, water cycle and climate sensitivity, which is important because the whole point of climate modeling is to better have climate energy description water description, because that influences the energy balances, and then these two then influence the climate evolution, so climate sensitivity. So, these are very important processes that must be represented as best as possible, so that these things, which is our final goal, is achieved as best as possible. So, uncertainty in parameterizations is of course a major source of model output uncertainty. The more we can better parameterize, the more we can better predict our model. Now, we will just in the next two slides we will have an introduction of atmospheric and oceanic GCMs. This is our atmospheric model. So, AGCM will simulate the three-dimensional atmospheric circulation. So, we see this three-dimension x, y and z direction, and there is a 3D grid box. So, these are the grids in x, y, z direction. This is a 3D grid box, and there is exchanges, and this box can have CO2, dust, all the chemicals, and the exchange is being happened in all the three directions. Simultaneously, there is incoming radiation of course through this box also, and there is a back radiation of course through this box also. So, and then the earth is rotating. So, this all of this is under rotation. So, the flows will also be adequately calculated. So, AGCM will solve the primitive equations in this rotating sphere and will include the parameterization for radiation, clouds and convection, the boundary layer turbulence and the large scale precipitation. When we are doing atmosphere only model, then we will define the sea surface temperature, so that we can parameterize the exchange or transfer of energy between atmosphere and oceans without solving the model for ocean. So, we will be sea surface temperature would be a given, that means the air model is being forced by the sea surface temperature. Similarly, we have here now the ocean grid model. Here we have again this ocean 3D grid box in the rotating sphere, and the exchange is happening in x, y and z directions. This ocean is driven by of course ocean circulations, and the boundaries of land will govern how the water is being transported, energy is being transported, and then this interacts with a given atmosphere in terms of water vapor, heat and momentum exchange with the atmosphere. So, the ocean general circulation model OGCM simulates the three-dimensional ocean circulation, which is governed by the momentum equation, continuity equation and the heat and salinity conservation, and will represent the wind driven circulation and this thermohaline circulation. Generally, the ocean circulation has to be operated or operates on a longer time scale than the atmosphere. After atmosphere and ocean, we have the sea ice models. So, of course, sea ice is an important component of the climate system. It simulates ice growth and melt. So, we can have ice, snow and then different fluxes, different temperature profiles, and in the ice itself we may have brine pockets. So, the sea ice model will simulate ice growth, ice melt, the thickness of the ice and the transport of the ice. This becomes important because ice is strongly involved in the albedo feedback, and also it influences the exchange between the atmosphere above and the oceans below. So, sea ice tremendously influences the overall energy budget of this particular locations and actually the whole earth in general as a consequence. After sea ice, we can look at the land surface. Land surface scheme represents the exchanges between land and atmosphere. So, that is sort of intuitive. The processes include parameterization of soil moisture and runoff from soil, runoff of water from soil, evapotranspiration, the snow cover on the land, the effects of vegetation on climate, the land processes in. So when we have these land processes will influence the surface energy balance and the hydrological cycle, which of course then influences the energy balances of atmosphere as well. So then we have the interaction or the output of the land surface models. Then we have the coupled atmospheric ocean GCMs, which will couple atmosphere, ocean, and also sea ice and land in some cases. So depends on, maybe they will say AOGCM or they will say a fully coupled GCM. So coupling will occur via few things. It will occur via dynamic exchange of heat, exchange of water, exchange of momentum. And this will allow for the simulation of the internal climate variability and the long term climate change. Now, when we have descriptions of different AGCM, OGCM, sea ice model, land surface model and the coupled AOGCM or the fully coupled GCM, we are looking for the initial and boundary conditions. So, all these models will require some initial conditions, which would be the initial state of atmosphere and oceans, for example, and if you have other ice and land, then everything. So, initial conditions. Then what are the boundary conditions? Boundary conditions could be the solar forcing from outside the earth, so solar forcing, and also the state of greenhouse gases maybe. In some cases we can have this as initial condition and the greenhouse gas change itself, which would be also sometimes called the earth system model. In GCM maybe they can say that the GHG is a given. Ocean initialization in such models is very important because of the long memory of the oceans. Sometimes these spin up integrations are required. After spin up, then the model is run for the actual test case. GCMs often require parameter tuning. The aim of the tuning is to improve the realism of GCMs. What they are predicting is actually close to reality or representing better the reality, and to maintain the physical consistency. We cannot have negative flows, for example, right. So, maybe this is an extreme example of having negative flows, but the physical consistency should be maintained. So, tuning can help to improve the realism and the physical consistency of the model. The model validation or evaluation is done by and it is essential to compare the model output with the observation and reanalysis of the data. If the model is good, it should be able to reproduce the observations, and then you can say I can go and predict the next some years, but the past should actually be matching, or the near term future should be matching for us to go forward in future and match the other things. Also, tuning and validation must be clearly distinct. We cannot change one parameter, make model equal to observation model output and say this is also a validation. Maybe we can divide the data. We can say I will use the model tuning for 5 years and the next 5 years I will use for evaluation, and then keep a distinction separate between tuning and validation. Now, so this is by models themselves, and as we know that there will be so many GCMs who will have different kind of parameter descriptions, different parameter tuning, somewhat different outputs also. When we have so many different GCMs, it becomes important to do a sort of intercomparison, so as to see if all the GCMs point to the same thing. If all the GCMs are predicting similar results, at least a similar trend, we know that the trend is good. What we may not know is one GCM predicts 100 units, other GCM predicts 120 units, then we say okay, the range could be 100 to 120, but the trend is positive, it is not negative. So, it is important to do intercomparison. So, in that case we have the climate model intercomparison experiments. So, CMIP coordinates the experiments across different modeling centers, different kind of institutes or research groups who are running these GCMs. The intercomparison project or this thing will provide same forcing scenarios, so that everything runs with the same emissions, let us say, or same radiation. Then multiple models are involved. This is used extensively in IPCC assessments. When we do this intercomparison, we are able to check model uncertainty. Which model is more uncertain in describing some output? What is the variability? How are the models differ from each other? So, what is the difference, magnitude difference, 10%, 20%, 30% between different models? So, model uncertainties can be evaluated. We can also check for robust climate signals. As I said, are all models predicting temperature increase? Are all models predicting precipitation increase? Then the question becomes, the precipitation of the temperature will increase. The only question remaining is, will it be 1 degree, 1.5 degree, 1.3 degrees? So, that will be the uncertain part, but the signal would be robust. So, the strength and limitations of GCMs we can go, that the strength is that GCMs are physically based and model or simulate explicit 3D dynamics, and they become suitable for future climate production, but the limitation is that they are computationally expensive. You need to have more time to run them. The resolution can be constrained because if you are trading between integration time, then maybe we have to talk about the resolution. And there is the uncertainty from parameterizations also. So, these GCMs sit between, if we were to place them, they sit between the full process based simple models, maybe like energy balance models or radiative convective models, and the fully coupled earth system models. These GCMs are suitable for detailed climate process studies, to do policy level climate projections, and our intermediate complexity models complement GCMs. This can be for doing long time scale studies and for doing the sensitivity experiments. So, with this we basically come to the end of the course, where we have studied the basics of climate modeling, energy balance models, numerical schemes to do to represent different processes, introduction to intermediate complexity models, and a short introduction to the general circulation models, which the student is encouraged to explore these intermediate complexity models and GCM models as they go and learn more and more theory, more and more details, more and more mathematics of representation, and they can carry on, and hopefully they will carry on and do an experiment more with climate modeling. With this, I thank you for your time.